You ever notice how some patterns just seem to pop up everywhere? I'm talking about things like the heights of people, the weights of apples, you name it. It's almost like nature has a favorite blueprint it loves to use over and over again. Well, today, we're going to pull back the curtain on that exact blueprint, the normal distribution.
So, let's just jump right in with a question that sounds pretty simple. Imagine you've got a chicken egg. What's the probability that it weighs exactly 72.9 grams? And I mean exactly, not 72.91, not 72.89, but 72.9 with an infinite number of zeros after it. What do you think the odds are?
Get ready for this, because the answer, and this is going to sound a little weird at first, is zero. A flat zero. The probability is absolutely zero, and I know what you're thinking. How? How is that even possible?
Okay, so here's why. It all comes down to a concept called a continuous random variable. Things like weight are continuous, which just means that between any two weights, say 72 and 73 grams, there's an infinite number of other possible weights, 72.1, 72.11, 72.115, and on forever. So when you're trying to pick one exact number out of an infinite list, well, your chances are basically zero.
Think of it this way. Even with the world's most perfect scale, when it says 72.9 grams, it's not really saying it's that exact number. It's really telling you the weight is in a tiny little range, maybe somewhere between 72.85 and 72.95 grams. We can't actually measure an exact point. We can only ever measure an interval. And realizing that, just that little shift in perspective is the key to solving this whole puzzle. So, if talking about single points is a dead end, what do? Well, we use this. This is nature's favorite curve. You probably know it as the bell curve, but its official name is the normal distribution, and it is the perfect tool for dealing with intervals instead of points. So how do we get a probability out of this thing? This is the brilliant part. It's not about how high the curve is. It's all about the area underneath it. So the probability of an egg weighing, say, between 70 and 75 grams is literally the amount of space under the curve between those 2 points. And that brings us right back to our original problem. A single exact point has no width, which means it has no area, which is exactly why its probability is zero. But why this specific shape? Why is the bell curve so incredibly common in the real world? Well, it's because the normal distribution tends to show up whenever a whole bunch of different, independent things are all affecting one outcome. Think about an apple. Its final weight isn't decided by just one thing, right? It's a whole mix of its genetics, the soil it grew in, how much sun it got, the weather, all these little pushes and pulls that, when combined, naturally average out to create that perfect bell shape. And what's really amazing is that every single normal distribution, it doesn't matter if it's describing apples or IQ scores, is completely defined by just two numbers. That's it, just two little parameters that tell you everything you need to know about its shape. Let's break them down. First up, you've got the mean, which we write with the Greek letter mu. This is super simple. It's just the center of the curve, the very peak. Think of it as the anchor point. And then there's the standard deviation, or sigma. This one tells you all about the spread. A tiny standard deviation gives you a tall, skinny curve because all the data is packed in tight. A big one gives you a short, wide curve because the data is really spread out. All right, now that we know about the mean and the spread, we can unlock this incredibly useful shortcut. It's like a cheat code for understanding any normal distribution, and it's called the 68-95-99.7 rule. It's super powerful. So here's how it works. You take your mean, and you take one step, that's one standard deviation, to the left and to the right. Boom. You've just captured about 68% of all the data. Now, take 2 steps out from the mean in both directions. You've now got roughly 95% of everything. And if you go 3 steps out, you've got a massive 99.7% of pretty much all your data. It's just that predictable. So let's go back to our apples for a second. This rule means that if we just know their average weight and their standard deviation, we can instantly know the weight range that almost every single apple in the orchard is going to fall into. No crazy math needed, just this one powerful rule of thumb. Okay, so up until now, we've been going in one direction, right? We start with a value, like an apple's weight, and we find the probability. But what if you need to flip that on its head? What if you already have the probability you want, and you need to find the specific value that goes with it? Let's look at a perfect real-world example. Imagine you're a biologist, and you're trying to protect a crab population. So a rule is made that says only the biggest 5% of crabs can be harvested.
This lets the other 95% stay safe to grow and reproduce.
So the biologist knows the probability he cares about, that top 5%. But top 5% isn't a ruler, is it? You can't measure a crab in percentages. He needs a hard number, a specific cutoff length in millimeters that fishermen can actually use. So how on earth does he find that value?
The tool for this job is called a quantile. Just think of a quantile as a marker, a signpost on our curve that's based on probability. So by finding the 95% quantile, the biologist can pinpoint the exact shell length and say, okay, 95% of crabs are smaller than this and 5% are bigger. Just like that, he's worked backward from a probability to a real-world usable number.
So let's wrap this up with the big takeaways. First, for anything continuous like weight or height, the probability of hitting one exact value is always 0. We get around this with the normal distribution, where the key is that area equals probability. And remember, that whole curve is defined by just two things: its mean, which is the center, and its standard deviation, which is the spread. And finally, the 68, 95, 99.7 rule is your best friend, your go-to shortcut for making sense of it all in a flash.
So there you have it. We've just unpacked nature's secret blueprint. And this pattern is absolutely everywhere, from biology and finance to psychology. So my final question for you is, now that you know what to look for, where are you going to see this amazing curve hiding in plain sight